Hello everyone, my name is Satyajit Padhy and I'm a PhD student at National Tsinghua University. The co-author of my presentation is Dr. Chou, who is my advisor too. The topic for my today's presentation is finding the optimal reconfiguration for network function virtualization orchestration with time-varied workload. In today's presentation, I'm first going to start by introducing network function virtualization. Then I'm going to explain you the VNF placement problem and the different approaches that are taken to solve this problem. After that, I'm going to introduce you to the VNF reconfiguration problem and our problem definition that is used in this paper. Then we will see how are the objectives and the approach being modeled in this paper to achieve the results at the end. So what is network function virtualization? Traditionally, the network hardwares or the middle boxes were efficient in processing network traffic for decades. Right now, since we have more network services being introduced to being processed, we need to seamlessly add more network functions in different network sites. But it is expensive and an expensive maintenance operation to actually maintain these network hardwares and to even add more hardwares for new network services. So network function virtualization proposes to actually softwareize these network functions into virtualized instances, which is called a VNF or a virtual network function. This virtual network function is instantiated in a proprietary server in data center. Because of this cloud native approach, there are several advantages. Not only it can have a reduced capital and operational expenditure based on traditional middle boxes, but it can even give us more flexibility in seamlessly adding new virtual network functions on the fly for new network services. Because of this, we can have a reduced resource and energy utilization, and it can be a big push for the future, like for 5G telecommunication. After knowing about network function virtualization, let me introduce you to a VNF placement problem and the different approaches that I've actually taken to solve this problem. In a typical VNF placement problem, we have an input which is called as a service function chain or a SFC. A service function chain or a SFC is a chain group of network functions. These network functions should be processed in the same specific order as it is defined in this SFC. For example, in this case, a DDoS protection network function can only be executed after a firewall network function has been processed. In the virtual network, we have virtual network functions or VNFs. Each VNF actually represents a network function of a particular type from a SFC. In here, our main task is to actually have a VNF placement solution where VNFs can be placed on physical servers in the physical network. What are the different approaches that can be used to actually do this VNF placement? The first one is a static VNF placement approach. Let's look at an example in my right-hand side here. We have three service function chains here. Each service function chain is a chain of three different types of network functions. In this example, the different types are actually represented by numbers like NF1, NF2, and NF3. The resource demand of each network function is actually given in brackets here. The flow of each traffic is color-coded, and you can see after we have placed the VNFs in the physical network, each SFC flow is being shown in different colors. If our objective is to reduce the energy cost by this placement approach, then based on the input of all the service function chain resource demands, we can come up with a VNF placement solution by placing as many VNFs as possible in a physical machine. Based on this bin packing approach, we can actually try to reduce the number of physical machines used, and in that way, we can actually reduce the energy cost. One important constraint is the resource constraint that we can take into consideration for this placement. The cumulative resource demand of all the VNFs should always be less than the physical capacity of a physical machine. Now, in today's generation, the workload demands actually changes over time, and that's actually called a time-varied workload. Based on this increased resource demand for time-varied workload, the VNFs might incur resource violation. Because of limited resource capacity on the underlying physical machine, we can still try to reduce the energy cost, but a static solution is not sufficient for this. That's why a good solution can be a VNF reconfiguration solution. Let me introduce you to what is VNF reconfiguration actually. What are the different solutions that we can actually utilize to obtain reconfiguration, and how is that problem definition based on the problems that we have discussed before? The first solution for a VNF reconfiguration can be a scale up. So what is scale up? A VNF can actually increase its resources to address the increased resource demand unless and until there is enough resource capacity in the underlying physical machine. In this example, you can see that VNF 2, 3, and 4 have increased their resource demand or scaled up to address the new demand changes in network functions. However, in PM1, after VNF2 has scaled up, there are not enough resource quota left. So VNF1 cannot scale up here. In that case, we can opt for another solution that is called scaling out. Scaling out is the process of creating a new instance of an existing VNF. For example, here we have actually created a new instance of VNF1. After creating a new instance, a SFC flow can be redirected from the original instance to the new instance. Both these instances of VNF1 can now scale up and can actually distribute the SFC traffic flows across the two instances. Even after carefully redirecting some selective SFC flows to new instances, there might be some delay occurring, and we have to make sure that this delay does not exceed the maximum delay that is defined by the service provider. Another reconfiguration solution that can be chosen for obvious different reasons is VNF migration. VNF migration is the process of migrating the entire VNF from one PM to another. In this case, VNF1 is migrated from PM1 to PM3. After it is migrated, VNF migration can actually cause some downtime, and in turn, it can cause some delay. So rather than not violating the user response time, we can try to make sure that this delay is within the maximum delay a SFC can actually incur. So based on some important constraints and the problem that we just explained, let us see our problem definition. In our VNF reconfiguration problem, we have modeled it as a two-level placement problem. In this two-level placement problem, in the top level, we have actually tried to place the set of network functions from a SFC into VNFs. This placement is actually determined by a decision variable h, which shows the placement of a network function n belonging to SFC S being placed on a kth instance of a VNFJ at time interval t. In the second level mapping, we try to place the VNFs on a PM. This is determined by a decision variable x, which shows the placement of a kth instance of VNFJ in PMI at time interval t. Let's look at the first level placement problem. In here, the input is the SFCs with all the chained network functions, the resource demand, and the bandwidth requirement of that service function chain. Based on that input, we have an output of this problem as the placement solution between network functions and virtual network functions, and we can even try to determine the residual capacity or the resource capacity of each virtual network function based on the network functions it's going to process. In the second level mapping problem, we have an input as the VNF resource capacity, the PM resource capacity, and the status of a PM, if it is active or inactive at that time interval. The output of this problem is the placement solution, which is the value for the placement decision variable x, and even we can see the reconfiguration solutions that were chosen for the increased resource demand at that time interval. So some of the important considerations in our problem is that a VNF is multi-tenant in nature. That means it can try to process multiple network functions from various service function chains. One important constraint for that is the type of the VNF should always be equal to type of all those network functions it's trying to process. For example, a firewall network function can only be placed on a firewall VNF. Now, let's see our objective and approach, how we have tried to address this VNF reconfiguration problem. Our objective is to address the trade-off between reducing the energy cost and the VNF reconfiguration cost. Moreover, our objective is even to know which reconfiguration solution can be chosen in which scenario. Our approach is to come up with the integer linear programming formulation to get an optimal solution. Let's look at our ILP formulation and let's start with the constraints. Our first set of constraints are the resource constraint. In constraint number 1, we have the VNF resource constraint. The VNF resource constraint states that the cumulative resource demand of all the network functions that are being placed on a VNF should always be less than the total resource capacity of a VNF. So decision variable h shows if a network function is placed on an instance of a VNFJ. So the total resource demand of all those network functions that are placed on that VNFJ should always be less than the total resource capacity of that VNF. RNS, or the resource demand of a network function of SFC, is always given as an input to the problem. We have even mentioned in our solver that the type of the network functions that are being placed should always be equal to the type of the VNF. In the second resource constraint, we have the PM resource capacity constraint. The cumulative resource demand of all the VNFs being placed on a PM should always be less than the resource capacity of the physical machine. The resource capacity of the physical machine is given by this variable mi, which is already given as an input to the problem. Next, we come to the placement constraints. In constraint 3, we have the VNF placement constraint, which says that a VNF can be placed on an active PM only. Decision variable A actually says if a PMPI is active at time t or not. Based on this value that is determined, we can try to make sure that a VNF should only be placed on an active PM only at any particular time interval. In constraint 4, we should actually confirm that each VNF should be placed on one PM only. That means there should not be any redundant placements in any particular time interval across the pool of PMs. In our last set of constraints, which are the link constraints, we go to constraint 5, which is the link capacity constraint. Decision variable W shows the link placement from a virtual link to a physical link. The bandwidth demand from a virtual link connecting two neighboring network functions should always be less than the total bandwidth capacity of a physical link connecting two physical machines. This is shown by this equation right here. In constraint 6, we have the flow conservation constraint. In flow conservation constraint, we try to make sure that the total ingress traffic entering a physical machine should always be equal to the total egress traffic exiting it. In this equation, we try to make sure that two neighboring functions of a service function chain, if the virtual link connecting them is placed on a physical link connecting two physical machines, so we should make sure that the total traffic flowing through those links should always be equal entering and exiting a physical machine. And that is shown by this example or equation right here. In our objective function, our objective is to minimize the energy, migration, and instantiation cost. Let me break you down the energy and migration cost first. The energy cost is the cumulative sum of all the turned on active servers across time intervals. The migration cost is the change in placement of a VNF on a PM across time intervals. For example, let's say at time t-1, VNF1 is placed on PM2. But let's say looking at this example, at the current time interval, VNF1 is actually placed on PM1, which is a change in placement, and the VNF has been migrated. Each VNF migration is actually multiplied with a cost, that is the cost for migrating each instance of a VNF. Instantiation cost is actually creating a new instance of a VNF. For example, here a new instance of VNF1 has been created. If the value of the resource capacity that is given by the decision variable C changes from a 0 to a non-zero value across time intervals, then we can come to a conclusion that a new instance of VNF has been created. Each instance of VNF undergoes a cost that is required to create a new instance. Let's look at our results right now that we have tried to obtain in solving this problem. So in our simulation, we have tried to generate 60 service function chains. Each service function chain is a chain of 5 network functions. Each service function chain can be one of these 3 network services. This network services is actually a chain of 5 network functions with a bandwidth requirement. The resource demands are randomly generated for each network function belonging to SFC. The physical infrastructure, we have 50 physical machines connected with a 1 Gbps physical link. The solver that we have used is the IBM CPLX solver to solve our ILP problem. Let's look at the results right now. In the first result, we are trying to show you the percentage of reconfiguration solutions, that is the output of our ILP problem. In the x-axis, you can see the traffic arrival rate increases. In the y-axis, we show you the percentage of VNFs that are reconfigured, like migration, scale out, and scale up. In the initial traffic arrival, you can see that scale up is the most preferred choice by the ILP solver. And that makes sense because it can actually increase the resource utilization and even decrease the energy cost. But as the traffic increases, the scale up preference is lower because of the reduction or because of the downgrade of the initial server residual capacity. So because of limited resource capacity in the initial server, the ILP solver tries to prefer scale out more at higher traffic demands. Okay. We can even try to show that we can tune the ILP parameters in our objective function. If we want to prioritize a certain cost out of the 3 costs we have in our objective function, we can do that too by using the tuning variable. For example, if we prioritize the energy cost, you can see that the pro energy cost or the prioritized energy cost in the blue bar is less than the baseline cost. Similarly, we can even try to prioritize individually the migration cost and the instantiation cost. And as you can see that the blue bar is lower cost compared to the baseline cost that is shown in the red bar for different service function chains. In this way, we can show that our ILP objective function is flexible and we can try to prioritize different costs in different scenarios. At the end, we want to show the importance of the reconfiguration cost. In the x-axis, you will see that we have incrementally added different reconfiguration costs for the ILP solver. In the y-axis, you see the reconfiguration cost of each individual cost and the total cost that is shown in the purple bar. Initially, when the ILP solver is only aware about migration cost and oblivious of the other reconfiguration solutions, the total cost is the highest. But as we keep on adding different reconfiguration solutions to the ILP solver, the solver makes smart decisions and hence gives a lower reconfiguration cost if we add the 3 reconfiguration costs here. In this way, we can show you the importance of adding the 3 costs that we have added in our ILP formulation for giving us the least reconfiguration cost and the energy cost. So, as a conclusion, I want to say that reconfiguration solutions are highly beneficial for time-varied workload. There can be a trade-off between reducing energy cost and VNF reconfiguration cost. We have proposed an ILP formulation for this VNF reconfiguration problem. Moreover, we have even used a 2-level placement solution to define our problem. From the experimental results, we have come to a conclusion that the preferred reconfiguration solution is scale up. But as the traffic increases and the residual capacity of the initial servers reduce, scale out is the most preferred solution. As a work in progress, we are currently implementing a heuristic solution to solve for a large case problem. Thank you again for listening to my presentation, and please don't hesitate to reach us if you have any questions.